Hey everybody, now we're going to study the energy stored in a capacitor. As charges compile on the parallel plate capacitors or any capacitor in general, then you can use this charge later on. This means that this is kind of like energy that you can use on. So as capacitors store charges, they are actually storing energy, all right? And now, let's say we charged up a capacitor. We just take the parallel plate capacitor as an example. There are many different types, but this is a capacitor that we're looking in. So this is a parallel plate capacitor, and parallel plate capacitor has a distance d between the two plates, and there is a electric field, and of course there is a potential difference. So if I put a potential here, V, and I want to measure that potential difference, it's going to be the same as the voltage here. All right. So we know that the electric potential energy, we need to find the electric potential energy, we know that the electric potential energy is equal to the work required to transfer charges from one point to another, and that's equal to the charge times the voltage difference. Okay, so if you are here and you measure the voltage between this point and this point, you're going to find it's V. If you go halfway between here and here, you're going to measure half voltage difference. If you go on the same plate, the voltage difference between here, this point and this point will be what? 0. So as you can see, it's a linear relationship. As you go away from one plate to the other, the voltage increases from 0 to full V. Okay, what this means that this voltage is going to be the average. So if we find W is going to be equal to Q, the average voltage between 0 and full V is basically what? Half voltage. So W, which is the energy stored in a parallel plate capacitor, is equal to 1/2 Q times V. So that's actually the energy stored in the capacitor. Now we also learned that Q is equal to C times V. Now let's maybe take this Q and put it here. So then W becomes 1/2. Q is C times V times V. So W becomes 1/2 CV squared. That's another form of the energy stored in a parallel plate capacitor. Okay. All right. Is there another form? Yeah, you bet. Q equals CV, which means that V equals Q over C. So I'm going to take that one here and write it down like this. So W is equal to 1/2 comes as it is. Q comes down as it is. Now V is equal Q over C times Q over C. So I end up W is equal to 1/2 Q squared divided by C. And that's a third form of the energy stored in a capacitor. Now, which form should you use? It depends on the problem. If a problem gives you the charge and the voltage on a capacitor, then you can use this one. If a problem gives you the capacitance and the voltage of the capacitor, you can use this one. If a problem gives you the charge and the capacitance, then you can use this one. So it depends on the form of the problem. Okay, and actually, as we are figuring this out, we're finding out that the energy of a capacitor is not a useful form of kind of like a value to look for when we are trying to understand what energy the capacitor holds. So we came up with another quantity that we need to study, which is the energy density. The energy density is more useful than the energy in general. Why? Because basically capacitors have sizes. We need to know how much energy we can store per volume of that size of the capacitor. All right? And let's do that. So now let's look into the energy density. Okay? So the energy density, I'm going to write it down here, is basically the energy the capacitor can have per volume. All right? Now, we know, let's take this equation for example. The energy of the capacitor here is equal to 1/2 C 1/2 times C times the voltage square. Okay? All right, so now what we can do with this is we know that the capacitance for a parallel plate capacitor is equal to kappa epsilon 0 times A divided by D. You can tell that it's easy to memorize because the capacitance increases with the area, increases with epsilon 0 or epsilon 0 on kappa, and decreases with D. So, all right, so now let's, when we know that also V is equal to E, the electric field, times D. So I'm going to put these two quantities here. So energy is equal to 1/2 C is equal to kappa epsilon 0 A divided by D, and V squared is equal to E squared times D squared. Now, D squared with D goes away, all right? We have D times A, so if I go back up here, so this is D, right? And the surface area of the plate is A. D times A gives us what? The volume. So I'm going to call this the volume, all right? So if I go back here, D and A gives us the volume, so I'm going to take this whole thing here, if I may. Energy is equal to 1/2 kappa epsilon 0 times E squared and times the volume. All right? Now divide by the volume and divide here by the volume. Okay? Volume with volume here cancels. Energy over volume, we called it what? Energy density. So if I want to put this equation in a tight, nice place, I can say that energy density is equal to 1/2 kappa epsilon 0 times E squared, where kappa is the dielectric constant, epsilon 0 is the permittivity of free space, E is the electric field. And this is a good equation to know. Right? Thank you very much.